Good morning, everyone. Penultimate Chem 1 lecture. Thank you guys all for coming. I mean, I do it anyway, but it's nice to have some people here. One of the downsides of being fully online is you don't get to interact with people. I'm glad that some of you feel that that's an important part of this, and it is. As I've said many times, you really don't understand something until you can explain it to someone else. That's the litmus test. Actually, that's interesting. I said litmus test there. Does anybody know where that phrase comes from? Yeah, it does come from pH. I didn't even occur to me until I just said it. There's something called litmus paper. It's just got indicators on it. You dunk it in a solution, it turns color, tells you what the pH is. So apropos the moment, here we are finishing up our discussion of acids and bases today. We've gone through an entire titration curve. We're focusing on the buffer region. Buffer region is the most important region for you all going into biological sciences and MCB, molecular and cell biology, and polyprotic acids. Most of the compounds in your body are polyprotic acids. So let's head right in there to where we left off. I rushed through a chem quiz yesterday, but I'll stop and go through it a little more slowly today, because buffers are the most important thing that you'll take away from chem. It's the things that'll show up in your next courses. So this is NH3 ammonia solution. When you put it in water, it forms NH3 weak base and NH4 plus, the conjugate acid. And we know now, whenever you have a combination of about equal concentrations of an acid and a conjugate base, that makes a buffer, and that resists change in pH. So we saw that last time. The question is, if I want the buffer to be a basic buffer, to buffer a solution above pH 7, what should I add to my NH3 solution? Strong base, salt, or strong acid? So one of the things you'll have to do when you get into biology and you're working in the laboratory is you will want to buffer your solutions that you're doing your chemical reactions, or you're growing your bacteria, or whatever you're doing. And if you want to buffer at a certain pH, you need a compound that will buffer at a given pH. And what is the property of the acid that tells you where it will buffer, at what pH it will be the strongest buffer? Don't shout it all at once. The pKa. When the pH is equal to the pKa of the acid, that's where it will be the best buffer. So you can look at a list of acids, pick one where the pH is equal to the pKa, and if that's where you want to buffer, that's the acid, weak acid to pick. So we'll look at this one. So I've written here, I did the old reverse thing on you, like I always suggest you do, and sometimes is helpful. Look at things from both directions. I'm putting this base in, but I wrote the weak acid equilibrium. So I put the weak acid reacting with water to form the base. And I'll say this many times, it does not matter which equilibrium you write down, they all are held in solution. All equilibria are satisfied at once in solution. So you can pick any of the equilibria that you like to work with and work with that. The reason I chose this one is the pH, the way we calculate pH, it is the pKa of the weak acid. So I want to think about the weak acid anyway. I've written it in reverse because we're starting with this, and we want to convert it into this. So we're starting with this weak base, but we need to make some of the weak acid. turn half of it into the weak acid, so we're in the buffer region. So that answers the question immediately. If it's going to be a buffer at all, I have to have the conjugate acid. I have to turn half of these particles, half of these molecules, into the acid form. So it kind of answers the question. You have to add acid to do that. Is it pH greater than 7, though, if you did that? It really is the only choice. You can only buffer around the pKa, so hopefully the pKa of this is above 7. And it is. We've seen it many times. K for this reaction is something like 10 to the minus 9. So going in this direction, it's 10 to the minus 9 is the K, so the pKa is around 9. So that'll buffer around 9. All I have to do is get equal concentrations of those two chemicals, or those two forms. The pKb doesn't help you with the buffer, but that is the pKb going in this direction, although it would be reacting with water if it were the Kb. These two form the buffer, so I have to add H plus to get there. The pKa of NH4 plus is indeed 9, so if you can get these two concentrations about equal, it will buffer around 9. So you have to add acid to make that happen. So let's talk about polyprotic acids, and we bring this up because, oops, apparently the animations are a little off here. Oh yeah, geez, forgot. This might be all messed up. I was just working on this. Polyprotic acids, not super complicated, but you can have more than one acidic proton. And I think you know already, biological molecules get quite large. DNA, what does that stand for? Deoxyribonucleic acid. So your DNA molecules, each one of them has potentially has acidic protons on it. So many protons. All you have to do is just keep track of all of their equilibria. That's not so hard. Each one of them has an individual K. You can treat them kind of individually. So let's just look at that. Each proton that comes off will have a tendency to come off based on the equilibria of the ions involved. So each acid has a pKa. Each proton has a pKa, is the way to think of it. So, and in general, as you pull them off, the acid gets weaker and weaker and weaker. It's harder to keep pulling them off. It's harder for the protons to leave the acid. So initially it might act as a relatively strong acid, but it'll get weaker and weaker as you continue to pull off protons. So the first equilibrium is, and now I've taken the water out. The first equilibrium is for carbonate. This is the carbonic acid that we made yesterday with the carbon dioxide and water. So this carbonic acid, these two forms are in equilibrium, and the pK is different enough that taking this proton off is different enough that these kind of act independently until you've shifted all the way over to mostly this base form. But it has a pKa of 6.1, so you could sketch the titration curve already. You know the pH has to go through the pKa at the middle of the buffer region. So that's a point on the titration curve that you get for free. And I could plot out just this part of the titration curve. But then what would happen is this would start acting like an acid. It can also give up a proton, but a much, much weaker acid. But that is a point in a buffer region where these two ions would buffer. So I think what you see what's going to happen is you'll get two buffer regions. This buffer region here, the pH will be equal to pKa1, so pH 6 here at half equivalence as you titrate along. And then you'll convert this into this, and you'll have an equivalence point where you've converted all of these to those right here. And then you'll start a new titration of this compound, CO3, you'll take those protons off, and it will buffer here at pKa 2. So, relatively straightforward. Indicators, those color-changing compounds, are polyprotic acids. That's how they work. So, when you take a proton off, the various protonated states are different colors. It's just handy. So, as you take off protons, this is thymol blue. Again, I'm abbreviating it. I'm just putting thymol with the protons that come off. It has two acidic protons. One comes off. It's red when both protons are on. When you remove one proton by titration, it turns yellow. And when you remove that proton by titration, adding strong base, it turns blue. So now you know that these things happen at specific pHs. Animation's all off because I was just mucking with it, sorry. This equilibrium will hold around pH 2. This equilibrium will hold around pH 8. So when the pH gets bigger than 8, you should expect blue. The pH between 2 and 8, you should expect yellow. And the pHs 2 and below, you should expect it to be red. So pretty easy to understand now that you understand the pKa and how that defines the titration curve. Right here at pH 8, there's an equal concentration of the yellow and blue form right there. That's what half equivalence is. Right here at pKa 2, there's equal concentrations of the blue, or the red and the yellow. There's very little blue. Okay? Lovely, straightforward, easy to understand. We'll just talk through this. This is a great chem quiz in the fall. We would spend more time on this. But here's thymol blue. Here is that crazy compound that I was telling you about. And you can see some acidic protons in there, but that's not crucial to us. This is just an interesting thing. So a pi to pi star transition. So we've been talking about molecular orbitals. And you can go from a bonding to an antibonding orbital, pi to pi star, and you can see there's lots of pi molecular orbitals. You know, double bonds are constitute a sigma bond and a pi bond. So you have a pi bonding network there, and you're going to go from pi to pi star transition. And you know there are these absorbances because they're colored. They're in the visible region. You can see them literally happening. So which, if you had to choose 1, 2, or 3, these are the 3 transitions that cause the 3 colors. Which is the absorption that's predominant at pH 10? Which one makes it blue? Which one of these make it blue? Well, you would tell yourself, well, if I had to pick, I know it goes red, yellow, blue. So if I want the solution to appear blue, should it be the smallest transition, the medium transition, or the biggest transition? Just anybody. Highest energy, medium energy, lowest energy, if I want the solution to appear blue. Largest? Anybody, we could turn on the machine and you could vote. Largest is your first thought, for sure. Blue, highest energy photon. But you have to think, oh, it's blue solution, so if it's absorbing the blues, it wouldn't look blue. So just have to think all the way through it. It's probably absorbing down here in the red, and that's why it looks blue. Again, this is too complicated for this summer and for anything you'd see on the exam, but just reminding you, and it's a fun way to remind you, the solution is not blue because it absorbs blue. The solution is blue is because it absorbs red. Okay? That you need to know on the exam, as you've had already questions about that on the exam. So pH 10, it's up there in the blue form. The pi to pi star transition collapses, and you have a lower photon energy absorbed. That's just nice. Okay, what is the predominant carbonate species? You have 3 carbonate species here. They depend on pH. You get this one at low pH, and then when you get to around pH 6, you get this one, and I think it was pH 8, pKa, no, it's 10, wasn't it? pKa 10, you start to get this one. So which carbonate species is present at the highest concentration at pH 7? Well, you can track them. You know what, at the equivalence points, what is the dominant species. You know there are a mixture of the species at the half equivalence points. So you can go right through that and say, I have these 2 transitions. One happens around pH 6, one happens around pH 10. So if I'm at pH 7, I'm about 1 unit towards the basic side. I'm pH 1 unit higher than this pH. 1 pH unit higher. I'm in here somewhere. So 1 pH unit higher, that means this basic form is there more than this acidic form, and much more than this form. So you can choose what's there, and you can also say, well, what's the protonation state in general? This is the most common form. There's a tiny bit of this, and there's a little bit of that, but the most common form is the -1 form of carbonate at pH 7. Okay? And you can do it the same way. You're far from this pKa. You're far from here. You're way down here. Again, gives you the same information that the most common is the HCO3. Why is that important? For a lot of reasons. But since a lot of you want to be biologists and doctors, let's talk about how your blood works. One of the things that keeps your blood around pH 7, it's not exactly pH 7, but carbonate, and you know your body is constantly producing carbon dioxide. And that is dissolved in your blood, so you have carbonic acid buffering your blood. And that works by 2 things that we understand. Buffering now, weak acids in solution, and the equilibrium between the gaseous carbon dioxide and the dissolved carbon dioxide, that equilibrium. So 2 things are happening at once. In your lungs, as you're breathing, the partial pressure of carbon dioxide is about 40 torr, so not very high. 700 torrs around an atmosphere, so 40 torr of partial pressure carbon dioxide in your lungs. And that equilibria, we know how that works. Partial pressure has an effect of fixing the concentration of dissolved carbon dioxide in your blood, in the solution. That stays at about 1.2 millimolar. So that's called Henry's law. I don't think we named it. We might have named it. But this is just your heterogeneous equilibria. So your lungs are helping you maintain this concentration. The carbonate, or the carbon dioxide, is converted into carbonic acid very efficiently in your blood by an enzyme, big protein, carbonic anhydrase. Keeps turning this into this. And then this can start to do the buffering. So the carbonic anhydrase and blood buffering system maintain this concentration, removing 1 proton, this equilibrium, maintains that concentration around 24 millimolar. So what kind of pH does that lead to? One more thing. Your kidneys are also working. So your kidneys, one of the most fascinating organs in your body are the kidneys. I encourage you to go into renal medicine if you go that way. The kidneys, the distal renal tubules in your kidneys, they are selectively permeable to ions. It's just unbelievable. The blood coming through, the kidneys can just sort out the ions that they want to remove from your blood. It just absolutely spectacular chemistry. And the kidneys can maintain this concentration in your blood based on other chemical things that are happening in your blood. So you have your lungs, you have an enzyme in your bloodstream, and you have the kidneys, 2 organs, and an enzyme working to keep this concentration 24 millimolar. And why are you trying to keep that concentration 24 millimolar? You look at the titration curve for the carbonic acid that we've had already, and we know the 2 concentrations of, or the 2 pKa's, and what you find is, well, I know that the pH is going to be determined by this pKa and these 2 concentrations. So the concentration of CO2 is concentration of the acidic form is dominated by the lungs in this carbonic anhydrase, and it holds it around 1.2 millimolar. The kidneys are modifying the base, or maintaining the base form concentration. So these 2 concentrations are being mitigated, and you put those 2 numbers in there, 1.2 for the acid form and 0.24 for the base form. And what you see is the blood is buffered at around 7.5. So take-home lesson, very beautiful biochemistry that you can understand through equilibria, through enzyme kinetics, and through the function of your kidneys to maintain. All your body's trying to do is do a buffer thing, trying to maintain weak acid and its conjugate base in the right ratio in your blood. All that machinery just to do that. I guess some of you might be riding along in ambulances and doing that kind of stuff as well. Have you ever seen, and maybe you've seen this on TV, there'll be a person who's hyperventilating. They're breathing really, really fast, like that. And one of the solutions for that, that you see on TV, is they say, you're hyperventilating, and that's actually dangerous because it lowers, if you're breathing out very fast, it dramatically lowers this concentration, partial pressure of carbon dioxide. You're breathing it out too fast. And that's going to cause hyperalkalosis in your blood. Your blood pH is going to change dramatically. So it is kind of dangerous if you hyperventilate for a long time. Your blood pH will change. So you'll see, I don't know, has anybody seen this or in real life or in TV? They say they take a paper bag. It looks like the person is maybe gasping for breath. They're not losing air. They're breathing too fast. It's hyperventilation. So you take the paper bag, and they breathe into a paper bag, and that stops that. Always paper too. You can imagine. You wouldn't want to use plastic, right? Somebody's already doing this. You don't want to put a plastic bag over their face and get into a worse situation. You can see the ambulance driver arriving. Would you like paper or plastic with your hyperventilation today? Choose the paper. What does the paper bag do? Well, if you're breathing in and out of the paper bag, now the bag is capturing the carbon dioxide that's going out, and it's going back in. So you can maintain that equilibrium with the paper bag and prevent the hyperalkalosis. But, yeah, theoretically. So, in general, the whole procedure tends to calm the victim as well. Just breathing into the paper bag just relaxes them, and the hyperventilation usually stops. But you could see maintaining that partial pressure by breathing into a bag would maintain this and maintain blood pH. There you go. Popular culture and medicine and chemistry all coming together, as it should in the last days of class. Other polyprotic acids. We already talked about DNA. Your amino acids are, many of them are polyprotic. They're all monoprotic amino acid. Well, they're all, technically they're all diprotic, because this, depending on the protonation state of the amino acid part, this NH can act as an acid as well, if you were to protonate it, for instance. So these are just two pictures, and this is aspartic acid. There's a proton that could be, that's attached there. I have it, I'll write over here. I've written the form, the negative form, where this one is gone. This one, this proton can either be there or not, and I've drawn it on, and there could be a proton here, too. But you know there's two forms, on and off. So the way I've drawn this is I've drawn these two protons removed, and when they're removed, you have the anion left over. So you have charges there. And I have this protonated. This proton is on. And, oh, I guess I was going to do that in discussion. Interesting enough. Do it here. What you can say, well, if you are at pH 7.4, what is the protonation state of your amino acids? Well, now you know. If I've written the pKa's here, pKa of that proton is 3.9, pKa of that proton is 10, pKa of this proton is 2. So if you're at pH 7, which form dominates? Well, if your pKa is 3.9, you're very much more basic than that at 7. So your titration curve has a 2A pKa of 2 and a pKa around 4, but you're way up here at pH 7. So you're at the basic form of this. The proton is removed, and you're the basic form of this. It's all, the protons are all removed. And you can see how important that is. That changes the whole charge state of the molecule. There's a positive charge there and two negative charges there. That's going to affect everything that's happening in your cell very dramatically. If there's a negative charge there and you want to do some catalytic action, you've pretty much got to account for the fact that at pH 7, there's going to be a negative charge there. And that's why it's so important that your blood is buffered. If you had any old pH, you wouldn't know if there was going to be a proton there or not. So keep it buffered, and you know what charge state you're going to encounter. So that's why this is all so vital. This is another example, histidine. Here are two other examples, lysine and tyrosine. You can see all the various pKa's of the various groups and how their protonation state would vary based on whether it's a protonated or deprotonated form, the positive, negative, or neutral form of the enzyme or the amino acid. Why does that matter? Well, here's horseradish peroxidase. And what this is a gigantic molecule. Have you guys ever seen pictures like this? What you're seeing here, this ribbon, that's the backbone of a giant molecule. And there are, I don't know what horseradish peroxidase is. It's probably 100,000-ish molar mass. So there's amino acids all along this chain, a couple thousand of them. And what you're seeing here are how the chain of amino acids folds up into this complex structure. And that complex structure allows this horseradish peroxidase. We can do this reaction, but I didn't get my act together. We can do this reaction in class. It's going to trap this complex, this smaller molecule, in this cleft here. So it's important that this molecule has this structure. And what's holding together that structure? All the things you've learned about. The hydrogen, oops. There's hydrogen bonding, stabilizing this. There's plus, minus interactions with amino acids, stabilizing that. All of these structures are stabilized by all the intermolecular forces that you've learned about and the fact that the pH determines the charge state of all those amino acids on that chain. That's what locks this in. It's what allows it to recognize this cofactor molecule in here. So if this weren't happening, your proteins would unfold and be useless. So you have to maintain pH, you have to maintain hydrogen bonding, and you have to maintain these various charges on your amino acids to make that go. Okay, lesson of the day. Complicated three-dimensional structures depend on all these intermolecular forces, hydrogen bonding, and the various charge interactions for these compounds. We already did this, but I'll just talk through it again. What is the charge at charge on the cysteine at pH 7? Well, here I've drawn all the protons attached, and I've said this has a pKa of 9, that has a pKa of 2. So at pH 7, this is the acidic form. That one's going to be the basic form. pH 2, this will be the basic form. This one, pKa 9, pH 7 is on the acidic side of pH 9. This will be the acidic form. And that NH3+, you recognize that as that ammonium weak acid. That one will have a plus charge. That one will have a negative charge. This is the base form. So that proton is gone, and that's negatively charged. The whole charge on the molecule is 0 at pH 7. I think that's all we wanted to say. Yep. Bunch of just nuts and bolts calculations there. So the last thing we'll talk about here in Chem 1 is electrochemistry. And you don't have to take a ton home from electrochemistry. All we're trying to get to is what are cell potentials? What is the voltage? What is the, and it's interesting, it's cell potential, it's also free energy potential, same kind of potential. So we're just going to talk about that in general. And basically, we're going to phrase it all in terms of ions. If you're going to talk about ions, which of those is the most thermodynamically stable? So you can imagine, here I have some water. I could put a piece of zinc metal in the water, a piece of copper metal in the water, and zinc ions can form, and copper ions can form. So if I prepared these in the standard state, what would be the concentration of these ions? Please shout it out. What's the concentration of these ions in their standard state? 1 molar. So I could prepare that in the standard state. The metal, solid metal standard state, this metal just has to be there. Piece of solid metal, that's its standard state, and 1 molar of each of them. The question is, which of those is favored, the metal or the ion? Metal or the ion. So how can we rank those? thermodynamically. Well, what's happening there is this is an oxidation, if I write it this way. So we formally define oxidation as an increase in oxidation number. The oxidation number increases from 0 to 2. Something else that could happen is a reduction. Not very confusing there. A reduction is a reduction in the oxidation number from +2 to 0. Either of those things can happen. They can go either way. The question is, thermodynamically, which one is favored, the metal, the ion, the metal, or the ion? How do these things, how are they accomplished? Well, clearly there's some electrons involved. If the zinc goes to zinc ions, 2 electrons were removed. And so another definition of oxidation is removing electrons. And we saw that when we calculated oxidation numbers, didn't we? We said, if you're going to look at the oxidation number of the central atom, have the more electronegative element remove all the electrons from it. And you were able to calculate the oxidation number of that central atom. Reduction is adding electrons. So, reducing the oxidation number, how do you reduce it? Well, add a negative number. That's a reduction. So those are the ways to remember what's going on in oxidation and reduction. We want to know which direction these go. For which orientation are k's greater than 1 or standard state free energies less than 0? I will tell you, I've written it the answer way. In this case, the ions are favored, and in this case, the metal is favored. So in this case, you would form the metal. This concentration would be reduced. Free energy says form the metal. This case says form the ion. But here's the thing. That doesn't really happen in solution. Electrons just don't go flying around in solution. So if you put copper metal and copper ion at 1 molar, nothing would happen. Again, thermodynamics says that's the tendency to go there, but you have to give it some way to do that. And this is the problem. Free electrons just don't float around in solution. You have to have something to grab those or give you those. So what happens is oxidation and reductions always happen in pairs. Those 2 electrons are these 2 electrons. I'm going to just take my electrons and give them to you. If I give you my electrons, I am reducing you. I'm a reducing agent. If I pull your electrons away, I'm an oxidizing agent. I'm oxidizing you. So let's just put them in the same beaker. Now there's a pathway for this to happen. In the same beaker, you could imagine the copper metal encountering the zinc surface and finding those 2 electrons that it wants on that zinc surface, the surface of that metal, and at the same time, a zinc ion going out into solution. That process can happen now that they're in the same beaker, and it does happen. That tells you that thermodynamically this wants to go this way and this wants to go this way. That is the spontaneous process. We call that plating out. The copper plates out onto the zinc strip. So thermodynamically favored direction is for these 2 electrons to be the same 2 electrons. Zinc forms zinc ions. It has these 2 electrons essentially waiting for copper ions to come over here and form copper metal. And you'll see the copper metal just form right on top of the zinc metal surface. So you could keep track of the concentration. If you did this, you'd notice the concentration of the zinc ions go up. Zinc ions are formed spontaneously. The concentration of the copper ions go down because the metal forms spontaneously. And that's the favored direction. This leads to K greater than 1. First, we have to write the reaction for which that's the K greater than 1. But you can already see it's probably going to be the reaction where products and reactants look like that. So let's just do that. The reaction we see is copper ions in the presence of zinc metal will form solid copper on top of the zinc metal and zinc ions. That is the reaction quotient expression for that reaction. And I'm telling you that that K is greater than 1. I've written it in the spontaneous direction. So if you start at the standard state, 1 molar and 1 molar, you should expect this concentration to increase. If you start at the standard state, this ratio is 1, right? That's a Q, right? I can make Q anything I want. I can put 1 molar and 1 molar in there. And if I do, what happens? Well, I know K is bigger than 1, so it's going to go towards equilibrium. That's going to get bigger. That's going to get smaller to get me a number bigger than 1. K tells you where you go from the standard state. K tells you where you'll go from any state. Any Q that you make, you can compare to a K and see where you'll go. But the definition of K is start in standard state, which way do I go? Towards products, K bigger than 1, towards reactants, K less than 1. Spontaneous, towards products, delta G negative. Not spontaneous, delta G positive, back towards reactants. That's our review lesson for today. So we call this thing, now it's going to start to get a little, you have to keep all the definitions constant here. This is a reduction reaction. Copper metal going to copper solid because, or the copper ion going to copper metal because the oxidation state of copper is reduced. As that reduction happens, this copper ion is grabbing electrons from something. So it's pulling electrons off of something. So the copper ion itself is called an oxidizer because it gets reduced. So there's that, all that verbiage to keep track of, unfortunately. I'll tell you, on the exam, you're not going to have to keep track of the verbiage. I'll show you what you need to do on the exam in a second here. Reducer and oxidizer. So they come in pairs, just like conjugate acid, conjugate base. In this case, you're moving electrons around. In the acid-base case, you're moving a proton around. You can't see the electrons being moved around. The electrons don't show up here. Acid-base, the proton shows up. Okay? So conjugate pairs similar to acid-base chemistry. But here's the beauty. This is what runs our entire civilization. Those electrons, copper ions really want those electrons. Thermodynamics says, give me electrons. The zinc metal is saying, heck, I'm willing to give up electrons and form zinc ions. So those two things, those two synergistic things want to happen, and if they're in the same beaker, they happen. But here's the fantastic, amazing part that is the focus of billions of dollars of research right now. If I put them in separate beakers, it still wants to happen. Thermodynamics says, make copper metal and make more zinc ions. Thermodynamics says, do that. You have to give it a path to do that. Well, what if I do this? I put them in separate beakers, but I don't let the copper metal or zinc metal or copper ions or zinc ions touch each other at all. There's a salt bridge. This is ions. So there's a bunch of different ions, not these two. And if this concentration decreases, so this plus concentration decreases, the copper metal plates out, you can have some ions leak out of this salt bridge and keep the charge the same. So this same thing here. If you make zinc ions here, you can absorb positives or dissociate negatives out of the salt bridge. So this is just pluses and minuses, a salt there, a source of ions. You can do that, and then you do this fantastic thing. You say this wants to happen on this side, this wants to happen on this side. How do I make it happen? I'm going to draw the picture first. How do I make it happen? Come on. The electrons, these two electrons, need to end up over here. And thermodynamics says, any way I can get them there, I'll take it. Remember, pathway does not matter. Thermodynamics says, give me those electrons. So what do? I make that happen by connecting them with a wire. I let the electrons go through a wire, and they want to go through the wire. And if you're making electrons spontaneously move through a wire, what have you done? You've created current. So the free energy release is now giving you useful work. And that useful work will light up your light bulbs, it'll power your computer. It's doing it right now on your laptops. This process is happening on your laps right now. There is some pair of oxidation and reduction separated, and you're forcing electrons to go through a wire, and they want to go through there so badly that you can get a little work out of them as they pass by. So the free energy of that reaction makes batteries. And batteries are the most important technology in the world right now. As you know, we can make as much energy as we need in modern society. And it's easy. Solar, wind, wave, energy, all these natural sources are great. But what do you do if the wind isn't blowing and the sun isn't shining? You want to store the energy. If we could just store it, we'd be fine. So the best way to store it is in batteries, because believe it or not, when the sun's shining, what do? You make this go the other way. And then when the sun stops shining, you let it go back this way. So you can make this happen. And of course, lithium-ion batteries, you have them all here. It's a lithium-ion system, the lithium metal. And lithium ions are vital to this going on. In fact, it's lithium on both sides, kind of. Lithium here, and you just kind of charge up one side of it and let it go back the other way. So finding ways to store electrical energy is the most important thing in society today. I was driving out to Utah. I like to go to Moab and mountain bike and ski, but and I come up over this rise, and there's a huge plain in front of me, and in the middle of that huge plain, in the middle of the Utah desert, there's this giant, glowing, bright as the sun thing on the top of this tower, hundreds of meters tall, in the middle of the desert. You can't even look at it. It's like the eye of Sauron. It's like you can't look at it. It's just blindingly bright like the sun. And I'm going, what the devil is that? I mean, it has to be out there because you cannot look at it. So as I drive by, there's this big pedestal, and all around it are mirrors, and they are parabolic mirrors, and they're focusing the energy of the sun, the light of the sun, right up on that top little thing there. And it's getting hot like the sun. The mirrors are so efficient that it's glowing hot like the sun. And what's happening up there? Believe it or not, they're melting sodium chloride, salt. They're melting table salt, which melts at around, I don't know, you guys know, around 2,500 degrees, probably pretty hot. I don't know off the top of my head, but some thousands of degrees it takes to melt salt.
800 C.
800, only 800 C. Huh. Yeah, 1500. Yeah, I was thinking, yeah, in Fahrenheit. 1500 Fahrenheit, yeah, 1,000-ish degrees Fahrenheit. And they melt it, and then what do? Well, now it's molten sodium chloride. You bring it down, and you use it to boil water, and you run a turbine, and you make electricity. And it's easy to store the molten sodium chloride. When the sun's down, you make enough hot sodium chloride, you can run that turbine all night. So a brilliant solution to this. The bad thing is it does have to be out in the desert because no one can look at that. Don't look at the light. But a brilliant solution to doing this, and just all free. The sun is going to melt the sodium chloride all day. So go to a sunny spot, and easy to do it. Solar energy in a really clever way that thinks about the storage issue in advance. Just make hot molten sodium chloride and run your turbines all night on your sodium chloride. Anyway, you can calculate this voltage. You get about a volt of potential from that. The cool thing, and this is the important thing, or one of the important things, this isn't cool. This is just the notation. I don't care if you can write. This is cell notation. If this were the fall semester, you'd have to learn how to do this. I don't care. I will give you the cell notation. This just says there's zinc and zinc ions on one side of the battery, and there's copper metal and copper ions on the other side of the battery. And in the middle, all these lines are phase or physical barriers. So that's a phase difference there, metal ion, physical barrier here, physical barrier there, metal and ions. And in between them, this double line indicates the salt bridge between them two. On this side of the cell, a reduction occurs, and on this side of the cell, an oxidation occurs. So we catalog these things. You probably were probably gonna say, Mark, how do we catalog them? We should have a standard to measure them all against. So all these various half cells, this copper, metal, copper ions, zinc, metal, zinc ions, those are half, each of them is considered half of a battery. So we measure all the half cell potentials relative to a standard electrode potential. And it's actually a weird one. It's hydrogen ions and hydrogen gas. So the way you do that is you take a platinum electrode, that's a neutral electrode, that is, that doesn't form any ions. It just gives a surface for hydrogen gas to turn into hydrogen ions. So you can make this happen, bubble in hydrogen gas, and you can make hydrogen ions out of it. If you make hydrogen ions, what happens to the pH as you start bubbling this in? It goes up or down. It gets more acidic, for sure. You're adding protons. Gets more acidic, the pH goes down. Low pHs are higher pH, more acidic. Leaks. Got an exam tomorrow. I know, it sucks. All this comes so fast. It gets acidic. If I made this the standard hydrogen electrode, you probably guess that I better make this in the standard state, right? So what's the standard state? What's the concentration of H+? 1 molar. What's the pH? Well, what is 1? 1 molar, you have to take, you would do it on your calculator, right? You could take minus log of 1 molar. What would you get? 1 is, remember, 1 is 10 to the 0, isn't it? So the pH is 0. Okay? The pH in the standard state, 0, because 1 molar H pluses. So I make this cell, and then I just pair the other cells with it. Oh, and of course, you'd have to have 1 atmosphere of pressure, and you'd have to have 1 molar to make it the standard electrode. Oh, look at that, I even wrote it down, pH 0. So now you just pair your other cells with that. You say, okay, I'll make my little battery, and this will be the standard half, and I'll attach all the other halves to it, and I'll measure the voltage. And that's what I do. So you take a copper ion at standard state, make sure that's 1 molar or it doesn't work, and attach it by a wire to that platinum electrode, and then you just measure the voltage there. How much do the electrons want to go this way or this way? And for this one, okay, just put your salt bridge in. You can write these half down. If you do, you find you measure a voltage of 1/3 of a volt when you do that. And remember, you have to have 1 molar, 1 molar, 1 atmosphere for that to get that 1/3 of a volt. Okay? If you do it with the zinc and the zinc ions, zinc metal and zinc ions, it turns out the current wants to go the other way. I think you probably would have guessed that. The copper wants the electrons, the zinc wants to give them up. So the voltage goes the other way. Current wants to flow the other way. So the standard helps us quantify these free energies, these how much does that reaction want to go? Okay. Now you can calculate the voltage of an entire cell. You take this number left, or the right number, you subtract it from the right. Here's a half cell, 0.34 volts. Subtract away this half cell, 0, and you would get a voltage for the entire battery. So if you did this one, voltage on the right side minus the voltage on the left side, it would be 0.34 volts minus 0.76 volts, so plus 0.76 total. You'd get about that volt, about 1 volt that we saw happening there on the last slide. This is our zinc and copper metal cell. That's all I want you to be able to do on the exam, I think. You might convert it to a free energy as well, because you know how I love my free energies, but it's easy. So what we do is we make tables. We just rank all these half reactions. None of these reactions happen by themselves. You can't have free electrons floating around. You have to pair them up to make them go. You have an oxidizer and a reducer. One thing gives up the electrons, the other thing takes the electrons, and these tables tell you kind of how it goes. It says, well, this one really wants to go this way. It's got the plus voltage. This one wants to go the other way. It wants to make zinc ions. So you could tell if you paired the copper ions and copper metal and zinc metal and zinc ions, the overall reaction would be make copper metal and zinc ions. This one goes this way, this one goes this way. So the ones that have the negative voltages tend to go in the reverse direction. The ones with the positive voltage go as written. This one we just define to be 0 volts. And remember, this is all thermodynamics. We can set 0 anywhere we want. Voltage is a state function. Okay, that means these are stronger oxidizers and these are stronger reducers as you go up and down. I'm not going to make you do that mental gymnastics on the exam. You don't have time to absorb all that. I just want you to be able to look at a reaction like this, see what's going on, understand that that's 2 half cells. It's copper metal going to copper ions and zinc metal going to zinc ions, and then look back and say, which direction would it go? Well, copper going to copper metal, that's the spontaneous direction. Zinc ions going to zinc metal, it's spontaneous in that direction. So this plus that will give you that plus that. So that's all you have to be able to write down. You should be able to look at a table like this, write a reaction that will happen in the spontaneous direction. So you add this one and the reverse of that one. and that gives you that. I don't care if you can write this part. You get a voltage, and of course, if you write this one and the reverse of that one, you would add the voltages. This one and the reverse of that one. The reverse of that one is plus 7.6. So that plus that gives you this 1.1 volts. And you can convert it into a free energy very simply. And it's beautifully related. It's just, it essentially is the free energy. A couple constants. This N is the total number of electrons transferred. So this is a 2 electron transfer. So 2 electrons. F is just a constant, it's Faraday's constant. It's the charge on a mole of electrons. Okay? So that is all you will have to do on the exam. You'll look at a, I think on the exam, it's just the picture is a battery, and there's one electrode on this side, one electrode on that side, and you just have to write the spontaneous reaction that happens or something like that. Or get this number by looking at the battery and saying, oh, it'll go this way, and it'll go that way with that much voltage and that much free energy. Something that you're probably excited to see is that minus sign there. Not many of you are excited about anything anymore. It excites you because it was bugging you that usually when we were saying something is spontaneous, that meant a reduction in free energy. So since these numbers are positive, you got to bet that there's going to be this negative sign here. So this, if you just talked about the free energy, if it's spontaneous in that direction, you better get a negative free energy out of your free energy calculation. Okay? So I know how relieved you are to see that happening. Okay, so let's put copper metal in sulfuric acid. This will make H pluses. So you're going to have copper metal with H pluses. And you've seen copper metal, H pluses, that's a half cell in there somewhere. We're going to do it all in one beaker, though. So these are the potential things that can happen. Copper wants to pick up electrons and form copper metal at plus 3,4 volts. Hydrogen ions can accept electrons and form hydrogen gas. The things that we have, what we have in that beaker is this and this. So we got this, but that doesn't want to go back this way. And we have this, and this is kind of indifferent. But the fact that you have copper metal and this indicates, well, nothing is going to happen. What you want is copper ions to pick up these electrons, but you don't. You got copper metal, and you have these ions. So you haven't made a battery. You just put that and that in the same beaker, and that didn't do you any good. This is what would happen, or this is what you put in the beaker, those two things, but you get a you get a positive voltage for that happening, because you'd add those two together like that, but it's positive going this way, and you have these two things. So it's spontaneous going that way, delta G negative, because the voltage is positive. These are the two things you have, and that number tells you it's not going to go back this way. So it's going to stay like that. So those are already the favored state, and nothing happens. If you mix those two things together, boring. You guys can enter a thing if you want here, I guess. Did that show up for you? You're here. You might as well get your last or your second to last credit. I'll turn off the mic. Okay, off we go. And now let's just do it the other way. I think you're going to guess copper didn't do it because copper essentially wants to be the copper metal. Zinc wants to be the zinc ion. So you're probably going to guess if I put a zinc rod in there in sulfuric acid and make those H pluses, it will go. And of course it does. Same analysis. You have that cell potential, half cell potential. You have this one. And those two cell potentials reverse and add. So you get, basically, you better cancel out electrons or no reaction is going to happen. If I reverse this one, I better reverse the sign of this one, add them together. And I see that positive voltage again. That means negative free energy. That means the spontaneous direction is this way. And these are the two things I put in the beaker. That means these are the two things that will form spontaneously. Okay? So, the answer there, I get both of them. Okay, this is just more of the same. I'm not going to go through all this because, I got to give you guys a break. I'm not going to just tell you a bunch of stuff. I mean, you can do this. It's the same thing. I do want to talk about this one, though. So what if I did, because we told you a minute ago, lithium on both sides when you do your lithium ion battery. How can that be? Well, this is how that can be. Don't change the metal, change the concentration of the ions on one side. Okay? So this isn't exactly how the lithium ion system works, but high concentration here, low concentration here, that is sufficient to cause an increase in voltage. Thermodynamics says this is the standard state, and you know that copper wants to form the copper metal thermodynamically. You give it a chance because what you have here is high concentration and low concentration. So you can create the potential for that reaction to go kind of by Le Chatelier's principle, just making the concentration really high on this side and making it go to this side. So another way to think about this is you can always think about a battery, take all this stuff apart and mix them together in one beaker, and the reaction should go. Okay? If you took all this apart and mixed them together in one beaker, you would get an intermediate concentration of copper. That same thing wants to happen, is thermodynamically favored, even though they're in different beakers. Why is that thermodynamically favored? Why is mixing the high concentration and low concentration together and getting the medium concentration, why is that thermodynamically favored? That's entropically favored. It's entropically favorable to have these things mixed up together at equal concentration. So that cell is entropically driven. It's driven by the concentration equalization. Entropy, a real force of nature there, creating the free energy that that goes. And as you know, free energy is, delta G is minus T delta S of the universe. It is the change of entropy in the universe. That's what delta G tracks. And if the entropy of the universe increases, that's a spontaneous process. And having those two things mixed together makes that go. Okay? So I think that's all we need to say. Let me just go through that. The rest is just I was just going to tell you about it going the other way, but we already did. And I don't care if, I'll just tell you, it can go the other way. Well, I'll put the picture up and then tell you. If you want, the electrons naturally want to go this way. But if you put a bigger battery or something that's making voltage, you can make it go the other way. Like when the sun is shining, photovoltaic cell there, put a voltage and make it go back this way. And then when the sun stops shining, it'll go back that way for you and give you your voltage back. So that's the take-home lesson for you guys that want to go. And I encourage you, if any of you, I hope I've inspired one person to do more chemistry. Probably scared everyone away. But if I've inspired just one person to study chemistry, go to graduate school, and figure out how to build big, badass batteries, that would be great for the world. So I hope somebody in here will go do that. Okay, I am giving the discussion today, so bring your questions for the exam. Tomorrow we have a all review. I'm going to talk more about biology and how that interacts, but everything about biology that we talk about will be a topic on the exam. So we'll just go through equilibrium and acid base and electrochemistry in a biological setting, much like we did with the blood buffer there. And we'll get those concepts, and then we'll have time at the end for more question and answer tomorrow. Okay, good luck studying. We'll see you guys, unfortunately, at 11 or whenever that discussion is, and tomorrow night.